So, we are back looking at rule based production systems. In the last few sessions, we saw this kind of a cognitive architecture which is used for problem solving, in which the user or the programmer has to only specify the rules, and the system which we call as an inference engine takes care of picking the rules, matching them with data, and selecting one rule to apply, and keeps doing this in a cycle that we saw. The cycle, if you remember, was called match, resolve, and execute. Now, it's turned out that if you look at this from very basic principles, it is the match part which is the most expensive part essentially, because what do you have to do? You have to look at every rule, and every rule may have some number of patterns. So, you have to look at every pattern in every rule and match it with every working memory element which is a record in your working memory, or which is a piece of data. So, the number of patterns multiplied by the number of elements in the working memory is the time that you would spend if you did brute force match essentially. The other parts are relatively computationally cheaper. The resolve part basically takes the conflict set, which is a set of matching rules along with data, and has to pick one, and the execute part is even less expensive, that it has to take the selected rule and execute the actions on the right hand side essentially. And we saw some aspects of this which talked about things like what are the conflict resolution strategies. We saw that refractoriness, lexical order, specificity, recency, and mean sense analysis. We will look at them again in terms of implementation, and we want to now focus on what is a good way of implementing rule based forward chaining rule based systems essentially. So, we will look at something called the rate network and the rate algorithm that is associated with that. Just to begin with a little bit of history about this. The word rate itself comes from an old English word, right or rate, which itself is derived from the Latin word, which is actually curiously the same as this rate. But basically it means an anatomical mesh of network as of veins and arteries or nerves essentially. If you look at the definition given by Merriam-Webster dictionary, it is the same, a network especially of blood vessels or nerves essentially, and anatomical parts resembling or including a network. We will see that the implementation of our rule based systems is going to follow this analogy quite closely. Just as our blood vessels, they carry blood from our heart to various parts of our body carrying oxygen, and they come back to the heart to be replenished again and then go back into the circulation. In the same way, we will see that our implementation of the rule based production system, which is going to be called the rate algorithm, using this network called the rate network, is going to be very similar. We will distribute information, which is the new working memory elements that are being added into the system, and we will collect them together to trigger rules that are going to be applicable. So, a little bit of history, as I said. It was developed by Charles Foji, who was a PhD student at CMU, and it was part of his PhD thesis, and you can look up a paper published by him. It is easily available on the net. But it became more popular when the emphasis shifted from expert systems to business rules essentially. I have mentioned this business rules earlier, and the idea is that the business community at various kinds, they are interested in specifying the rules of when what should be done and things like that. They are not so much concerned in writing the algorithms which will implement those rules essentially. And when it caught on in the business community, then the rate net algorithm became very popular. So, most business rule management systems, that is BRMS vendors, developed their own algorithms which are known in elite circles as X-Rate or Uni-Rate. So, there were all variations of Rate. Rate 2 was developed by 4G himself, and it broke what is used to be called as the legendary Rate wall, which referred to the dramatic performance drop or degradation when the number of objects in the working memory increase. The whole game that we are talking about efficiency is that if you have a large number of rules and if you have a large amount of data, how to do this match efficiently, especially given the fact that the cycle says that it is a cycle in which you do the match every time, then you do resolve, then you execute, and you keep doing it again and again. So, if in every cycle you have to do match once with huge amounts of data, how does one manage? That is the idea. Rate 3 was an evolution of Rate 2 and developed by this company called Sparkling Logic, which use in their system called Blaze Advisor. And some of this history that I am talking about, I got it from this blog by Carol and Berlioz, who was working in Sparkling Logic essentially. Now, Rate NT. In those days, NT was a popular trademark extension, you might say. At one point, there was a operating systems called Windows NT, which came in the 80s as well. Anyway, so this Rate NT was the new OPS-J RateNet engine from Production Systems Technology, which is a company, uses the latest incarnation from Charles 4G. So, Charles 4G did the advancements in this thing, and he started this company and it became a big hit and all that. The engine works with Rate based, some people call it REIT, some people call it Rate. I prefer to call it Rate. So, Rate based business rule management systems, including those with IBM, Oracle and so on. As you can see, it was a very popular technology. They made it available to people licensed at $5,000 per CPU, or it could be used directly in the production systems technology applications. The new generation of this algorithm, which is called Rate NT, is much faster than Rate 3 essentially. From the academic community's point of view, unfortunately, we do not know why it is faster, and because it had become a trade secret by then and the company benefited directly from keeping it secret, it has not come into public knowledge, but it is a good problem that you can worry about and see how can we make the algorithm that we are going to discuss now a little bit more efficient essentially. So, what are the benefits that people got from using the Rate algorithm and the RateNet? Again described by Carol and Berlioz. The best usage of Rate network I have seen, she says, is in a business environment, which is to deal with alarms which come out of systems, correlation and monitoring essentially. So, she says that it is a stateful kind of execution where alarms are received over time. So, just imagine that you are monitoring some large network of things. In this case, they were monitoring networks or network management systems, and at some point some device somewhere would raise an alarm or would fail or something like that. So, the whole question was when to raise what kind of alarms essentially. So, the actual telecom network is made up of thousands of pieces of equipment which have to be kept in mind, so to speak, while processing the alarms essentially. There is no wonder that Rate outperforms brute force. You can't keep cycling through every piece of equipment or every piece of data that comes out of it essentially. So, when one alarm is raised on one router, the Rate network does not have to reprocess all the past events to realize that we have reached the threshold of 5 major alerts on the same piece of equipment and trigger the proper treatment essentially, and eventually providing a probable diagnostic. So, you can see that it is like pieces of data cropping up somewhere over your large network and you have to make sense of it essentially, and you do not want to every time a new message comes, you do not want to look at all the older messages again and again. And she claims that hours of processing time turned into seconds in network management systems essentially. So, you can see that it is clearly something which is worthy of attention of people who want to work in developing software which can be used in situations like this. So, let us now first turn our attention to what are the savings that we can do essentially. So, just to again recap, let me draw it here. Our cycle is simple, you do match, you produce the conflict set. So, let me put this in circle and then you do resolve, you produce a rule and then you do execute, and the output of this execute basically goes back into match essentially. So, this is a cycle that we are talking about. You keep going through this cycle. In every cycle you match all the rules with all the data, pick one rule, execute it, make the changes that you want to make in the working memory and go back and do match again. So, there are two kinds of savings that we can think of doing here. One is called savings within the cycle itself, and one which is we will call as intra-cycle savings, and the second is savings across cycles, which means from one cycle to next, what is it that we can carry forward so that we have to do less amount of processing. So, let us first start with intra-cycle savings, and we will go back to our simple examples. Here is a small example which is meant for grading. So, supposing faculty member is using some kind of a software for grading, and the software is a rule based software, then you may have rules like this. So, what does this rule say? The first pattern says that if there is a student whose name is n, whose roll number is r, remember that n and r are variables here essentially, because they come in angular brackets. So, these are applicable to all students and all roll numbers and everything. So, supposing there is a student essentially, the second one says that if that student, so remember that if you use the same variable name in the same rule, then it must match with the same constant essentially. So, if that student that we are talking about in the subject AI, he has got marks which are more than 59. Remember that this is the marks he has got, and this is more than 59, and this is less than or equal to 70. So, essentially between 60 and 70 if he has got marks, and if he does not have a grade, then you assign a grade C to that student. How do we do that? We do that by modifying this element and modifying the grade C, which was originally nil, we change it to C essentially. So, this is one rule which looks at the AI course and looks at the C grade. So, this is one rule for one grade in this thing, and likewise you can imagine there are other rules for other grades and other courses as well. Just to illustrate the idea, we will see shortly that we do not have to be so specific while specifying the rules, but this is just to illustrate the idea of how this whole thing happens. Okay. So, I may need this piece of the board. So, let me rub that off here. Hopefully, you remember what is the cycle that we are talking about. Here is another course, and in this case now the course is a different course. Let us say it is machine learning, and its cutoffs are 49 and 60, which are different from this thing, and this is also a rule for C grade in machine learning course. So, you can imagine that for every course, for every grade you could write such a rule, and then the whole system could go inside and you would enter all the data of all the students as to in which course how much marks he or she has got, and the system would do the grading essentially. So, we just take a tiny example here. In our example, we are just looking at a subset of the data. There are 6 working memory elements in this. Remember, these are timestamps 1, 2, 3, 4, 5, 6, and there are 2 students we are talking about, Sneha and Sunil. And we are talking about both these courses, because we are talking about both these rules. So, you can see that that Sneha has got in AI she has got 66 marks, in ML she has got 50 marks. Now, you can see that that both these grades kind of match, both these marks match these 2 rules that we have stated here. So, you expect that she would get C in both the courses, and Sunil has got 62 in AI and 69 in ML essentially. So, the AI course he should get a C grade. So, in all this data we expect to see 3 instances in the conflict set, but of course, Sunil will get some other grade, probably B grade or something, because 69 marks is more than 60. So, maybe that is in the B range, but that rule we have not shown here essentially. What we want to show is the intra-cycle savings that you can do if you implement the system properly. So, look at the first rule and with the first pieces of data. The first working memory element is that Sneha is a student. The third working memory element says that in AI she got 66 marks. Now, because 66 is between 59 and 70, it matches that second pattern, and the first pattern matches this, and that will go into the conflict set essentially. But it so happens that the second rule also matches for Sneha. Sneha has got, as you can see, 62 marks, 50 marks in ML, which is between 49 and 60. So, both these rules will match. In fact, for every student, for every course, some rule will match, because every course that they are doing, they would get 1 grade somewhere, and so there would be some rule matching that 1 grade. Now, what we are talking about intra-cycle savings here is that the first pattern in both these rules is same, and in fact will be same in all the rules. So, that if we match rule 1, then we match rule 2, then we match rule 3, and so on and so forth, we do not want to match the first pattern again and again and again. Okay. Having matched it once, we know that okay, there is a student called Sneha we are talking about. We should be able to cut down on the matches for the other rules. So, the question is, can we, for all the rules in which that pattern occurs, do the match only once? That would be the ideal situation. It is not just that the complete pattern should be repeated, even if part of the pattern is repeated, we would still like to share the work done in matching that particular pattern. So, if the first 3 attributes of a pattern are the same, then if we can match those first 3 attributes only once, then we are doing some savings. Now, notice that I use the word first 3, whereas I had said earlier that the order in which you mention the attributes do not matter. In fact, they do not matter, but this ordering that I am talking about, the first 3, will come through the implementation that we are going to shortly see essentially. So, the basic idea of intra-cycle savings is that if you can share the work done for matching different patterns, then go ahead and do so. That is the goal of intra-cycle savings. So, in this particular example, as I said, there are 3 rules which will match. The other rule that matches, shown in blue for Sunil, is saying that Sunil will also get a C grade in AI, because the working memory number 5 says that he has got 62 marks, and that is in the range of 59 and 70. The last pattern will match something, but it will not match a rule. It will not match one of these 2 rules. It will match a rule that we have not mentioned here essentially. So, as far as the data that we are seeing on this screen, the conflict set will get 3 rules. One says that Sneha will get C in AI, that is the first one here. The second one says that she will get a C in ML, and the third rule, sorry, the second one says that Sunil will get a C in AI, and the third one says that Sneha will get a C in ML essentially. So, that is one side of the story. So, as I said, this was just for illustration purposes that I used two separate rules to assign C grade for each course essentially. In practice, one does not need to do that essentially. You can just write one rule and that will take care of all the courses and all the grades essentially. But of course, you have to have additional data here. So, if you look at this rule and compare, this rule has got three patterns. The rule that we saw earlier, the two rules that we saw had two patterns. One pattern said that this is a student, and the second pattern says that this is the range in which C grade is given. Now, we have three patterns, and the first pattern shown here basically says that in some course S, which is now a variable here, earlier we had AI separate and ML separate, there is some low cutoff, there is some high cutoff associated with some grade G essentially. And whichever student we are talking about, if the low matches what is there in the first pattern and if the high matches what is there in the first pattern, then you should give the grade which is specified in the first pattern. So, there is an association between the first pattern and the third pattern essentially. The first pattern specifies the cutoffs and the grade, and the third pattern says that this student is within that range essentially. If you implement a system like this, then one rule will be enough to do all the work that you want to do. So, there were two students we talked about, Sneha and Sunil, there may be others, and then we talked about 4 courses here, but there will be other courses. For example, Sunil would have got a B grade in ML and other students would have got something. In addition, what the instructor or the user needs to do is to specify the cutoffs for every grade that she is giving in her course. So, essentially somehow these kind of working memory elements need to be added to the working memory. So, for example, if I were teaching AI, I would say okay, for C grade my range is between 59 and 70, for B grade my range is so on and so forth, and so every instructor would specify these ranges. You can imagine that you can build a software system whereby the instructor says okay, this is my course, these are my cutoffs, and here I am uploading the list of marks and do the grading for me automatically. Such systems are common. In fact, we use one system like this in IIT Madras, and the whole thing can work in a rule based fashion essentially. So, there is compactness to be achieved if you write the rules in a more general enough fashion essentially. Okay. Now, the other part we said was intercycle savings. Between cycles, can we do some saving of work essentially? And what is it that we are referring to? We are referring to the match part. We have said that match takes up predominantly the most amount of time in the cycle of match, resolve and execute essentially. So, let us look at this simple argument. Supposing there are 300 students in your institute and between them they have taken 1200 courses. So, let us say each student takes about 4 courses on the average. So, there are 1200 courses with 300 students, which means that 1200 grades have to be assigned essentially. And if you had this rule that we or rules that we had spoken about, there would be 1200 instances of grade assignment rule in the conflict set. Depending on whatever strategy that you have implemented for resolving those conflict, one rule would be selected and that rule would fire essentially. but the remaining 1199 rules are still matching, nothing has changed about the other students' marks or cutoffs or anything like that. The question is, why should we do that match for the remaining students all over again? And as we will see uh, shortly, the data network is a organization of data which allows us to do both this intracycle savings as well as intercycle savings in one go. It is quite a neat algorithm and definitely worth studying carefully. So, what is it that we are going to do? We are going to replace the brute force match. What is the brute force match? It says that take every pattern in every rule and match it or compare it with every working memory element in the working memory essentially. So, every pattern in every rule with every piece of data. So, you can see the amount of work that is being done is quite huge. Instead, we will replace it by a structure which is called the retail network. And what the retail network will do is that instead of taking the working memory as input, it would take only changes in the working memory as input, and instead of generating the conflict set as the output, it will only generate changes in the conflict set as the output essentially. So, you can see that what is happening here or what is going to happen here is that when the execute part of a rule happens, it says add certain working memory elements, delete certain working memory elements. They are changes in the working memory. So, those would be inserted into the RetainNet. The RetainNet, as we will see, is going to be a compilation of the rules. So, on the left hand side of the figure you have rules and working memory as input to the match algorithm. On the right hand side there are no rules, and that the reason is that the rules have been compiled into the retail network essentially. So, it only takes the changes in the working memory and produces changes in the conflict set essentially. So, we will stop here. I hope you will think about what we want to do and try to imagine how you would do this, but we will take it up in the next session, next video essentially. So, see you after hopefully a short break.